The next thing to talk about is the molar volume of a gas. This is perhaps exactly as it sounds, and that is the volume of 1 mole of our gas. So if we look at the ideal gas law and we solve for the molar volume of a gas at STP, we'll be plugging in 1 mole, a temperature of 273.15 Kelvin, and a pressure of 1.000 atmospheres. And when we solve the ideal gas law, we get a volume of 22.4 liters. This tells us that the volume of any gas at STP has a volume of 22.4 liters. The identity of the gas doesn't matter. Notice that in the ideal gas law, it's only the number of particles in units of moles that factors into our calculation, so that 1 mole of any gas at STP will have a volume of 22.4 liters. 1 mole of oxygen would have a volume of 22.4 liters at STP. 1 mole of argon at STP would have a volume of 22.4 liters. We can use this information as a conversion factor. If we have gases that are at STP, we can do calculations between moles and volume using that as a conversion factor. So we previously saw an example in our stoichiometry problem where we were able to convert from our 6.24 liters of CO2 at STP to moles using that as a conversion factor, and our answer was 0.279 moles of CO2. So if we want to calculate the density of a gas at STP, we know that the volume of 1 mole of any gas is 22.4 liters at STP. We also know that we can calculate the molar mass of a gas. So at STP, in order to calculate the density for a gas, we need the molar mass divided by 22.4 liters. So if I look at a sample of helium at STP, and I have 1 mole, my density will be 4.00 grams divided by 22.4 liters, which is 0.179 grams per liter. For argon, my molar mass is 39.95 grams. When I divide by 22.4 liters, I get a density of 1.78 grams per liter. For xenon, my molar mass is 131.29 grams, and when I divide by 22.4 liters, I get a density of 5.86 grams per liter. Notice that as the mass of my gaseous particles goes up, the density for my gaseous sample also goes up. In each of these samples, we have 6.022 times 10 to the 23rd atoms, but as my atoms become more massive, the density of my gaseous sample goes up. Also notice here that the volume unit that we're using in our density calculations is liters. In our gaseous sample, we have lots of empty space. Our particles are spaced very far apart in three-dimensional space. And so in order to have meaningful values for our densities, we're going to have that bigger volume unit of liters. Notice that if you compare a density of something like water to perhaps the density of argon that we see here, water's density is just about 1 gram per milliliter, and we see here that the density of argon is 1.78 grams per liter. So for gases, we have a much larger volume unit when we speak about their densities. So if we want to be able to calculate the density of a gas under any set of conditions, we can derive an equation using the ideal gas law. So if we rearrange the variables in the ideal gas law to have N over V set equal to P over RT. In order to calculate a density, we'll need units of grams per liter. And so if I look at the side of my equation that has N over V, I need to convert my moles to grams. And I can always convert my moles to grams by multiplying my moles by molar mass. So in order to keep the value of both sides of the equation the same, I'm going to multiply both sides of my equation by molar mass, and that gives me an equation where my density will now be equal to Pm over RT, where m is the molar mass of your gas. So if we look at some examples using these equations, you see at the top of this handout, we have your conversion factors that you've already been told you'll be provided with, but now we have two new equations. The first is the density equation that we just derived, where D is equal to MP over RT. Question number 1 asks us to calculate the density of xenon at STP. And what we already discussed is that when we calculate the density of a gas at STP, we need to know the molar mass and the molar volume. So if we look at the molar mass of xenon from the periodic table, we get 131.29 grams, and our molar volume at STP is 22.4 liters, so that the density of xenon at STP is 5.86 grams per liter. If we look at a second example, we can calculate the density of xenon at 742 millimeters of mercury and 45 degrees Celsius. So for this question, because we are not at STP, we have to use the equation where our density is equal to the molar mass times the pressure divided by RT. So for this problem, we will need to convert our pressure of 742 millimeters of mercury to atmospheres. When we do that, we get 0.976 atmospheres, which is the pressure we will plug into our equation. We will also need to convert our temperature of 45 degrees Celsius to Kelvin. And when we do that, we get a temperature of 318 Kelvin, which is the temperature that we will plug into our equation. So when we set up our equation, we have the molar mass times our pressure divided by R times T. And as you put this into your calculator, make sure you have parentheses around your denominator. And when you solve, you get 4.91 grams per liter. In question number 3, we're going to calculate the density of xenon at a pressure of 742 millimeters of mercury and a temperature of 100 degrees Celsius. In question number 2, we previously converted that pressure of 742 millimeters of mercury to 0.976 atmospheres. Now in this question, we have a higher temperature at 100 degrees Celsius, so that's going to be 373 Kelvin. As I plug into my equation and solve for the density of xenon, I get 4.19 grams per liter. Take a moment and compare the density values that you calculated in question number 2 and question number 3. What we see by comparing these two values is that at constant pressure, as our temperature goes up, the density of our gas goes down. And this is similar to why a hot air balloon works. In question number 4, we're asked to calculate the molar mass of a gas that was found to have a density of 1.43 grams per liter at 23 degrees Celsius and 0.789 atmospheres. So that as we look at the information given to us in the problem, we're looking to solve for our molar mass, we're given our density, our temperature is given to us in degrees Celsius, and when we convert it to Kelvin, we get 296 Kelvin. Our pressure is 0.789 atmospheres, which are the appropriate units to plug into our equation. So the equation as we derived it was that our density is equal to molar mass times pressure divided by RT. So in order to use that equation in this problem, we need to rearrange the variables and solve for the molar mass. When we do that, we find that our molar mass is equal to dRT over P. As I plug all of my information into the problem, I solve and get a molar mass of 44.0 grams per mole. As an alternative question, I could have asked you to identify the gas instead of asking you to simply calculate the molar mass. And if I asked you to identify the gas, you would need to calculate the molar mass and then look at the choices like you see here and compare your choices to your calculated molar mass. So if your choices were methane, xenon, argon, and carbon dioxide, you would have to calculate that the molar mass of methane is about 16. From the periodic table, you see that the molar mass of xenon is about 131, and the molar mass of argon is about 40. When you calculate the molar mass of carbon dioxide, you get a molar mass of about 44, making it the best answer to that question. Question number 5 says, a 113 milliliter sample of a noble gas has a mass of 0.171 grams at 721 millimeters of mercury and 32 degrees Celsius. What is the molar mass and what is the identity of the gas? We have a lot of information that's been given to us in this problem, and this problem is going to allow us to use the second equation that we see on the front of our handout as an application of the ideal gas law. And that is where we're going to substitute into the ideal gas law for moles for mass over molar mass to allow us to directly relate the mass or molar mass to the properties of our gaseous samples. So if we look at the information that has been given to us in the problem, our volume needs to be converted from milliliters to liters, so we'll plug in 0.113 liters. Our mass, 0.171 grams, can be directly plugged in for G. Our pressure of 721 millimeters of mercury needs to be converted to atmospheres, and we get 0.949 atmospheres. Our temperature of 32 degrees Celsius, when converted to Kelvin, is 305 Kelvin. So we have all of the information to plug into the equation, and you see the equation here. M equals GRT over PV, where capital M is the molar mass, and G represents the mass of our sample. And remember that this came from a derivation where N equals G over M, and we're substituting in. When you plug all of your variables in, and when you solve, you should get 39.9 grams per mole. So because we know our gas is a noble gas, we can look at the periodic table and compare the molar mass that we just calculated to the molar masses of our noble gases, which means we know the identity of our gas is going to be argon. As an alternative strategy, we could take the information given in the problem and we could use the pressure, volume, R, and T to solve for moles using the ideal gas law. If we solve for moles, we'll get 0.00428 moles, and we know that for any sample, if we take the mass divided by the moles, that will give us the molar mass. So in this case, if we take 0.171 grams divided by 0.00428 moles, we get 39.9 grams per mole, and we know the identity of our gas is argon.